Here we have this particular problem. We would like to prove that this infinite series is equal to this quantity at the right hand side. Here in this example we have a non-trivial infinite geometric series, which is this one, and we will use some techniques in order to derive this particular equation. So we have to rely on proving methods, so we will prove this statement over here. We start taking this sum over here. Now this can be written in the following way, using Euler's formulas. So the sign of kx is written in the following way. We know that these formulas are valid. This is the Euler's identity. So when we have e to the minus I theta, this is cos theta minus I sin theta. So for sin k of x, the sin k of x can be written in this way. Now we can write, we can take out 1 over 2i. We have the sum, so 1 over 2i is a complex number. And then we have this following sum. Of course, when we have a sum, we can break it into two separate sums. Like this. We can write it in this way. Now this can be written in this way, e to the power of ix over r, and this to the power of k. And similarly we do this for the other term. Now, as a reminder, we have that the sum of sum from k going to 0 up to infinity of alpha to the power of k is 1 over 1 minus alpha. This is the infinite geometric series where alpha needs to be strictly less than 1. So we can exploit this property here, and we can write it in this sum in a closed form like this. So it is 1 over 1 minus e to the power of ix over r. And here minus 1 over 1 minus e to the power of minus ix over r. Now we do some manipulations here, computational manipulations. Like this. Of course, here we can use the Euler's identity, again, the Euler's formula, to write it in a better way. There we go. When we have a complex number, we multiply by the conjugate complex number. in the numerator and in the denominator. So we will obtain 1 over 2 times I. So a big parenthesis here, r times r minus cos x plus I sin x minus r times r minus cos x minus I sin x over r minus cos x squared plus sine squared of x, and again here we have r minus cos x squared plus sine squared of x, and we close the parenthesis here. Now let me rewrite this in a more concise way. So I will rewrite this below because here it is quite it's not very convenient. So this is r times r minus cos x plus I sin x minus r times r minus cos x minus I sin x, and this is the denominator. We have this denominator over here. So this is r squared minus r cos x plus r I sin x minus r squared plus r cos x plus I times r sin x, and the denominator is r minus cos x squared plus sine squared of x. Let's see if we can get rid of some terms in the numerator. So r squared with minus r squared, they go away. Also we can remove these terms here. So we end up with 1 over 2 times I, 2 times r times I sin x over r minus cos x squared plus sine squared of x. We can so the 2 with 2 over 2 is 1. We can have these terms removed here. So we have r sin x in the numerator and r minus cos x all of it square plus sine square of x. So we go to the other page. This is r times, I will rewrite it, r times sine of x over r minus cos x squared plus sine squared of x. Now we have to do this, we have to expand the bracket here, so it's r squared minus 2 times r cos x plus cos squared of x plus sine squared of x. So this is r times sine of x over r squared minus 2 times r cos x, and we have this identity here that cos squared plus sine squared is equal to 1. So let's compare. It's r times sine x over 1 plus r squared, 1 plus r squared minus 2r cos x. It is one interesting example problem to do this kind of proof. It requires some steps to use the Euler's identity and also use properties of geometric series. So you write it in this way using Euler's identity, then you can split the sums. Then you can write it in this way to mimic this formula here. Then you do some trivial calculations. You multiply by the conjugate complex numbers. You do the computations that are required to be done in the numerator. And in the denominator also you do some computations, and then you end up with the desired result.